Somewhere in a quiet lab in the United States, engineers are testing a battery that behaves nothing like the one in your phone or car. It does not leak, it rarely catches fire the way older batteries can, and it may store nearly twice as much energy in the same space. For over a century, gasoline has powered the world because nothing could match its raw energy density, until now, when chemistry finally caught up. But the real story is not the battery itself. It is the decades-long race to solve one physics problem almost nobody outside a lab has heard of. That problem nearly stopped this technology before it started, and the way American engineers solved it may change how every car, plane, and grid works. Before we reach the breakthrough, you need to understand why building this technology was so difficult in the first place, for so many years. To understand that, we have to go back to the very same battery sitting inside your pocket, powering your phone right now, this moment. Every lithium-ion battery works the same basic way. Lithium ions travel between two electrodes through a liquid electrolyte that carries the electrical charge. That liquid is efficient at moving energy, but it is also flammable, and it is one major reason electric vehicle fires make national headlines. For decades, researchers dreamed of removing that liquid entirely and replacing it with something solid, safer, and capable of holding far more energy. In theory, a solid electrolyte would be lighter, safer, and dramatically more energy-dense than anything liquid-based chemistry could ever realistically achieve. In practice, it turned out to be one of the hardest unsolved engineering problems in all of modern materials science for over a decade. Early solid-state prototypes cracked under stress, degraded quickly, or simply stopped functioning after only a handful of charging and discharging cycles. Universities and startups around the world tried for years, and most of them quietly failed, ran out of funding, or shelved the idea entirely. But a small number of stubborn American companies refused to give up on this idea, even as skepticism grew across the entire industry. One of them is Factorial, a United States battery developer that spent years quietly refining its own lithium metal solid-state battery design. Their goal was never just a better battery on paper, but one that could survive real-world driving conditions, not just a controlled lab bench. Getting there required solving a problem most ordinary people have never even considered, something scientists simply call the dendrite problem. Here is the challenge in simple terms. When lithium metal charges and discharges repeatedly, it can grow tiny needle-like structures called dendrites over time. Those dendrites can eventually pierce straight through the battery's internal barrier, causing dangerous short circuits that once made this chemistry seem impossible to use safely. For years, this single unsolved issue was the main reason lithium metal batteries were considered far too dangerous for everyday consumer use. Solving it meant rethinking the entire battery from the inside out, questioning assumptions that had stood for decades of battery engineering. Engineers began experimenting with new solid electrolyte materials that could physically block dendrite growth while still letting ions move efficiently between electrodes. It sounds simple in description, but at a microscopic level, it is one of the most delicate balancing acts in modern materials engineering. Make the material too rigid and the battery cracks under mechanical stress. Make it too soft and dendrites simply break straight through anyway. Finding that narrow middle ground took years of patient trial, repeated failure, and a level of quiet persistence most companies never sustain. Some research teams tried ceramic-based electrolytes, prized for blocking dendrites effectively, but notoriously brittle and difficult to manufacture at any real scale. Other teams explored flexible polymer-based designs instead, historically weaker at stopping dendrite growth but far easier to manufacture consistently at volume. The eventual answer, for several American labs, was not one single material, but a carefully engineered combination of several working together. And then, in a single test drive, something changed that the entire battery industry had been quietly waiting years to see happen. In August of 2025, a Mercedes-Benz EQS test vehicle drove more than 1,200 kilometers on a single charge, without stopping once to recharge. That is roughly the distance from Stuttgart to Malmö, crossing an entire stretch of Europe, using nothing but one advanced battery pack. The battery powering that vehicle was not an ordinary lithium-ion pack. It used lithium metal solid-state cells developed by Factorial in the United States. Those cells were engineered in direct partnership with Mercedes-AMG's Formula One powertrain division, a team more accustomed to building engines than batteries. According to Mercedes-Benz, the new pack held roughly 25% more usable energy, in a size and weight close to the standard battery. For a technology once considered far too unstable for daily use, this milestone arrived sooner than most industry experts had honestly expected. But this achievement was not an isolated success story, happening in a vacuum, separate from everything else moving through the industry. Across the United States, other companies have been racing toward the very same destination, but approaching the problem from different technical directions. QuantumScape, another American battery developer, has spent well over a decade developing its own version of solid-state lithium metal battery technology. Their approach uses a ceramic separator instead of a liquid electrolyte, aiming to combine higher energy density with meaningfully improved overall safety. Every company chasing this technology is essentially solving the same core physics puzzle, just in a slightly different engineering way each time. And that quiet competition between rivals more than any single flashy announcement is genuinely what keeps accelerating real progress industry-wide. So what exactly makes a solid-state battery so fundamentally different from what already powers most electric vehicles driving on roads today? Think of a traditional battery like a sponge fully soaked in flammable liquid, where ions swim through that liquid to generate usable power. A solid-state battery instead replaces that liquid with a solid material, something closer to a crystal or an engineered dense ceramic layer. This single structural change removes much of the fire risk that comes from punctured, damaged, or severely overheated liquid-based battery cells. It also opens the door to finally using lithium metal instead of graphite for the battery's negative electrode, a long-desired engineering goal. Lithium metal can store significantly more usable energy within the exact same physical space than the electrode materials used in batteries today. Industry researchers now estimate that mature solid-state packs could eventually reach energy densities between 300 and 500 watt-hours per kilogram. Today's best commercial lithium-ion cells, by comparison, typically top out somewhere between 200 and 260 watt-hours per kilogram. In practical terms, that difference could eventually mean an electric vehicle capable of traveling over 600 miles on a single full charge. It could also mean dramatically lighter batteries for electric aircraft, delivery drones, and heavy long-haul electric trucks moving freight across the country. There is also a secondary benefit rarely mentioned in headlines: potentially faster charging speeds thanks to improved ion conductivity in certain solid designs. But impressive numbers written on paper do not automatically translate into real-world success once a battery leaves the laboratory and hits the road. Turning laboratory promise into something an ordinary customer can actually buy at a dealership is an entirely different and much harder challenge. That exact challenge is precisely where this recent breakthrough moment becomes so genuinely important for the future of this entire industry. For years, solid-state batteries existed almost entirely as small, delicate, lab-scale prototypes far removed from anything resembling real mass production. Building one single working test cell is one achievable thing, but manufacturing millions of identical, reliable cells is an entirely different problem. Solid materials simply do not make perfect physical contact with each other the way flowing liquids naturally do inside a battery cell. Even microscopic gaps between internal layers can meaningfully increase electrical resistance and noticeably reduce a battery's overall real-world performance. Solving that problem required entirely new manufacturing techniques, extremely precise material layering, and unusually tight quality control across every production step. This is exactly why so many earlier solid-state projects looked genuinely promising in theory, yet consistently stalled once engineers tried scaling them up. The recent progress shown by American battery makers marks one of the first times these designs have actually performed outside a controlled laboratory. A real vehicle, driving on a real road, covering serious distance without stopping, is a very different kind of test than any bench experiment. That is precisely why engineers across the entire industry are treating this specific moment as a genuine, meaningful technological turning point. Not the finish line by any means, but the very first real confirmation that the intended destination is actually physically reachable. So what could all of this mean for ordinary everyday life, assuming the technology continues to mature and improve over coming years? Start with electric vehicles first, since that remains where most of the current research funding and engineering attention is focused. Longer driving range could finally eliminate one of the biggest hesitations everyday drivers have about switching away from gasoline-powered vehicles. Faster, meaningfully safer charging could significantly reduce the range anxiety that currently keeps many hesitant buyers sitting on the fence. Lighter battery packs could also improve vehicle handling, overall efficiency, and even long-term manufacturing costs as production scales up over time. But the potential real-world impact of this technology reaches far beyond ordinary passenger cars and everyday commuter vehicles alone. Commercial airlines have long explored the possibility of electric propulsion for shorter regional flights across busy domestic air corridors. The obstacle has always remained the same. Batteries have simply been too heavy for the amount of usable energy they actually store. A lighter, denser battery could potentially make short-haul electric aviation genuinely realistic within the next decade of continued engineering progress. Long-haul electric trucking faces that exact same weight versus range problem, one that meaningfully better batteries could eventually help engineers solve. Even electrical power grids could benefit, using large-scale battery storage to hold renewable energy for use when the sun or wind is unavailable. Portable consumer electronics could also shrink in size while lasting longer between charges, though that likely remains far down the priority list. Defense and aerospace applications are also being quietly explored, where lighter power sources can matter just as much as they do in cars. None of these specific outcomes are truly guaranteed, but each one becomes noticeably more plausible as solid-state battery technology keeps improving. And that brings us honestly to the part of this story that most viewers and most headlines almost never actually hear about. Because this technology, as genuinely promising as it sounds right now, remains far from a finished, perfected, market-ready product. The first major challenge standing in the way is simply cost, and it is a significant one across the entire supply chain. Solid-state batteries currently require noticeably more expensive materials and far more precise manufacturing processes than traditional lithium-ion battery cells. Building factories capable of producing these cells at truly massive scale requires enormous financial investment and a great deal of patient time. The second challenge is manufacturing yield, meaning simply how many finished cells work correctly versus how many fail during actual production. Early solid-state production lines often produce a noticeably higher percentage of defective cells compared to well-established lithium-ion factories worldwide. Every single defective cell adds meaningful cost and slows down exactly how quickly this technology can realistically reach ordinary consumers. The third major challenge is long-term durability across thousands of charging cycles, not simply performance during one impressive long test drive. Real-world consumer batteries need to perform reliably for many years, enduring extreme heat, freezing cold, and constant relentless daily use. Researchers are still actively gathering long-term data on precisely how these new, solid-state cells physically age and degrade over time. The fourth challenge is scale itself, the difficult transition from small pilot production lines to genuine full industrial manufacturing capacity. Most independent industry experts agree that true solid-state batteries at truly massive volume remain unlikely before sometime in the early 2030s. Some hybrid or semi-solid designs may reach limited commercial production somewhat earlier, serving as a practical bridge toward full solid-state technology. There is also the ongoing question of raw materials, since some proposed designs still rely on genuinely limited global lithium supplies. That is one major reason researchers elsewhere are exploring alternative chemistries, like sodium-ion, as a complement rather than a total replacement. This is simply not a story about a switch flipping overnight. It is a story about steady, difficult, incremental engineering progress. And that measured honesty is actually part of exactly why this particular breakthrough deserves genuine trust rather than casual skepticism. Unlike flashy claims promising an instant miracle battery, this specific progress has been documented through real, verifiable testing and measurable results. Engineers involved in this research are not promising that gasoline simply disappears tomorrow or even within the next several years. They are demonstrating, quite literally mile by mile, that the underlying physics finally works reliably outside a controlled laboratory setting. So, naturally, where does this rapidly evolving technology actually go from here, over the next several important years ahead? Factorial has publicly stated its goal is achieving series production of these solid-state cells sometime before the end of this decade. QuantumScape and several other American developers continue steadily refining their own separate manufacturing processes in parallel, racing toward the same finish line. Automakers around the entire world are watching closely, some forming direct engineering partnerships, others cautiously waiting to see who scales first. Researchers are also actively exploring next-generation materials beyond today's designs, including advanced cathode chemistries that could push energy density noticeably higher. Some early experimental cells have already demonstrated energy densities approaching 600 watt-hours per kilogram under carefully controlled laboratory testing conditions. That number, if it can ever be reliably achieved at true commercial scale, could genuinely redefine what an electric vehicle is capable of. But scientists remain careful to describe this specific number as a future possibility, not yet a current guaranteed engineering reality. The gap between one impressive lab result and a dependable product sold reliably to millions of ordinary people remains genuinely enormous. Closing that stubborn gap is now the real competition, arguably more important than any single test drive or celebratory headline. Government-funded research labs across the United States are also quietly studying next-generation electrolyte materials that could feed future commercial designs. Some of that foundational work is happening quietly, years away from any public product announcement, yet still shaping what becomes possible later. Whoever manages to manufacture these batteries reliably, affordably, and at truly massive scale first may end up shaping transportation's entire next era. For well over 100 years, the story of transportation has been written almost entirely in gasoline and internal combustion. That story was built on a fuel so energy-dense that nothing else realistically came close for generation after generation of engineers. Now, for the very first time, American engineers are meaningfully closing that gap using advanced chemistry instead of traditional combustion. Not through one single miracle invention, but through years of failed prototypes, redesigned materials, and genuinely stubborn engineering persistence. The dendrites that once destroyed early lithium metal batteries have not disappeared entirely, but they have finally been controlled well enough to work. The dangerous liquid that once made batteries genuinely risky has now been replaced with something noticeably safer and considerably more energy-dense. And one long test drive across a stretch of Europe has shown the entire world that this is no longer merely theory. There remains a long road ahead between one successful prototype and a working battery sitting in every ordinary driveway. Costs must fall considerably, factories must scale dramatically, and years of continued real-world testing still genuinely lie ahead of us. But for the first time in decades, engineers are no longer asking whether this ambitious technology can actually work at all. They are now asking a very different question, simply how quickly it can be responsibly built and delivered for everyone. And that fundamental shift from open possibility to measurable progress may honestly be the most important breakthrough hiding within this entire story. Because the next time you fill a car with gasoline, remember that somewhere in an American lab, engineers are quietly working to end that habit. Not overnight and not through empty hype, but one carefully solved engineering problem at a time, year after year. The question is genuinely no longer if batteries can eventually replace gasoline as the world's dominant source of transportation energy. The real question now is simply who builds that future first, and how soon the rest of the world will be ready to follow.